So next is workbook question, that is from the chapter Optical Fiber, question number 14. The permittivity of water at optical frequency is 1.75 epsilon naught. It is found that an isotropic light source at a distance d under water forms an illuminated circular area of radius 5 meter as shown in the figure. The critical angle theta c, which is given, and the value of d in meter is. So it is given that this is the boundary or the interface which is separating the two medium, that is air and water. Now this is the normal, or here the light source is placed. This is the light source. It is given like this. This is the normal, and one wave is traveling, or the light is traveling from here and incident on this water and air interface. So some part of it is transmitted like this, and some part of it is reflected in this way. Similarly here also, symmetrically, the some part is incident and some part is transmitted and some part is reflected. Now if the light which is on the interface is incidenting with an angle theta c, it is making an angle theta c, and it is because it is incident with the angle theta c, it is actually parallel to the interface. Similarly here also. And the wave or the light which is incidenting making more angle than theta c is totally internally reflected. So this is the wave which is not even transmitted to the air, it is totally internally reflected. So we have got this figure, and how we can say that it is this light wave is incidenting with an angle theta c. So because this is the normal of the interface, this is the normal of the interface, and if this angle is theta c, so this angle should be theta c. So this light wave is incidenting on this interface making an angle theta c, and if a light making an angle theta c, so it does not go to the other medium, it goes it makes 90 degree to the normal and it goes parallel to the interface that we have already discussed while we discussing the ray optical theory. And when any light incident with angle greater than the critical angle, then it is totally internally reflected. So this is the light which is TIR, that is totally internally reflected. It is not even traveling in the second medium. So this is the figure which is given to us, and it is also given that it is making a circular area. It is making a circular area somewhere here with the radius 5. So at this point to this point, it is making like this a circular area on the interface. This is the circular region. This is the circular region. So whenever this type of question is given to you, there is another question this type in the chapter plane wave propagation practice question. You will find this type of question in which it is given that it forms a circular cone or something. So this is the circular portion which it is forming, and it is given that this distance is given to you, and this distance is 5 meter, and we have to find the distance d at which this light source is placed. So if you want to calculate the value of d, as you can see that we know this distance d, right? We know this distance, which is 5, and we have to find this distance, which is given as d. So we have to find this distance, this one, and this distance is given as d. So this is d or this is d. So we have to find the value of this d. That means this right angle triangle we can apply, where the angle is theta c is given. So if you apply the right angle triangle, so you will see that this, in the right angle triangle, this tan theta c is equal to 5 by d. So what will be the value of d? So the value of d would be 5 divided by tan theta c. So ultimately we have to find the critical angle. So what is the critical angle? So this critical angle is given by this theta c is equal to sine inverse n2 upon n1. That is the refractive index of the second medium to the first medium, ratio of refractive index of the second medium to the first medium. The second medium is in which the light is transmitted, and the first medium from where the light is generated. So light is moving from the water to air. So this N2 is the refractive index of air. This N2 is refractive index of air, and this N1 is refractive index of water. Now the refractive index of air, we know that it is 1, and we also know that the refractive index is given in terms of permittivity, so which is 1.75. We know that the refractive index n is equal to root over epsilon r. So here it is root over epsilon r, which is 1.75, which is given as 1.75. You can see from the question 1.75 epsilon naught. So this is 1 divided by root over 1.75, and if you take the sine inverse of 8, you will get the critical angle, which is 49.1. So critical angle is 49.1. So from here we can have the value of d, which is 1049.1, which is equal to 5 divided by 10 in answer is 4.33. So the value of d in which the light source is placed is 4.33 meters. So the correct answer would be 4.33. Okay. Now next is question number 15. So let's read that question. A typical relative refractive index difference for an optical fiber defined for long distance transmission is 1%. So the relative refractive index difference is given as 1%. When the core index, the core refractive index, which is represented by n1, which is given as 1.46. We have to find the value of numerical aperture. So what is the value of numerical aperture? So this numerical aperture is given by in terms of relative refractive index difference. You can directly write Na is equal to n1 into root 2 into delta. See how you can remember this formula. So you can remember this formula, this delta is equal to n1 square minus n2 square divided by 2n1 square. So this is nothing but del is equal to numerical aperture whole square, and this is 2n1 square, and hence the value of numerical aperture will be n1 into root 2 delta. So this I substituted here. This is the original definition of relative refractive index difference. So now let's substitute the values. So the value of n1 is 1.46, and this is root over 2 into 1%, this is 0.01. So let's find this value. the value of this numerical aperture is 0.206. 0.206. So this would be the answer. This is a numerical answer type question. Okay. So next is question number 16. Next is question number 16 to 18 actually, because this is a common data question. A step index fiber has a core diameter of 80 micrometer, a core refractive index of 1.62 and numerical aperture 0.21. So the diameter is given as 80 micrometer and the core refractive index N1 is 1.62 and numerical aperture is 0.21. So what is the acceptance angle, the cladding refractive index and the number of mode fiber can propagate if the wavelength is 0.8 micrometer is. So there are three questions associated with this data. So first question, question number 16 is very simple, the acceptance angle. So we have solved the question of acceptance angle. So the acceptance angle is given by theta A is equal to sine inverse numerical aperture. So this is sine inverse numerical aperture is 0.21, which is sine inverse 0.21, 12.12 degree. So I am getting the answer for question number 16 is 12.12 degree. Okay. So this is the correct one. This is the first answer. Now we have to solve the second question, which is question number 17, and what is that? Cladding refractive index, that is N2, and we also know that this numerical aperture is given by root over N1 square minus N2 square, and the numerical aperture is 0.21. The refractive index of core is 1.62 whole square minus N2, that is the refractive index of the cladding that we have to calculate. So what would be the value? So it would be 1.62 square minus 0.21 square. If I take the root over it, I will get 1.606. So the answer is of the refractive index is 1.606. That is the refractive index of the cladding. Now next one is question number 18. In the question number 18, we have to find number of mode the fiber can propagate if the wavelength is 0.8 micrometer. So the wavelength is 0.8 micrometer, we have to find the number of modes. So number of mode is given by number of modes is equal to V square by 2, where V is known as V number. So we have to calculate this V number. So this V number is given by V is equal to pi d by lambda into numerical aperture. So the pi is the constant, diameter is given 80 into 10 raised to power minus 6, and the wavelength is also given for the wavelength 0.8 micrometer. So this is 0.8 into 10 raised to power minus 6 again, and the numerical aperture, the value of numerical aperture is given as 0.21. So this 10 raised to power minus 6 will get cancelled and we get 100 here. So it is pi into 80 into 0.21 divided by 0.8, which is 65.97. This is the value of V number. Now the number of mode is like it is denoted by n. So 65.97 whole square divided by 2. It is 2176. So the number of mode is given by 2176. So this is the question number 18. Now next is question number 19. For a 3 micrometer diameter, that is the diameter is 3 micrometer. For a 3 micrometer diameter optical fiber with core and cladding indexes of 1.545 and 1.510, the cutoff wavelength is. So the refractive index of the core and cladding is given as 1.545 and N2 is 1.510. We have to find the cutoff wavelength. So cutoff wavelength is the maximum wavelength above which the optical fiber works in the single mode and the below which it works as a multi-mode. So the V is always less than equal to 2.405 for the single mode, and for multi-mode this should be greater than 2.405. And corresponding to the single mode we get the maximum wavelength. So the cutoff wavelength is given by this cutoff wavelength is given by this lambda c is equal to pi d upon V into numerical aperture. So the value of we should select as 2.405 because above this it works in multi-mode and below which it is in single mode, and that is the maximum cutoff corresponding to V is equal to 2.405. The D is 3 micrometer and the numerical aperture is root over n1 square minus n2 square, that is 1.545 whole square minus 1.510 whole square. And if you solve this, so we are getting 1.28 micrometer, 1.28 micrometer, and because this is a multiple choice question we are having the option B as the correct answer. Okay, so now we are having question number 20 and 21. Next is question number 20. Light pulse propagates through a fiber cable with an attenuation of 0.25 dB per kilometer. The distance through which the power of the pulse is reduced by 40%. So the power of the pulse is reduced by 40%, that means the 60% will be left. Okay, so the power is at any distance L is given by the peak value at z equal to 0 say, and e to the power minus 2 alpha into z. This is the relation of the power. So as it travels, we know that in the plane wave propagation we study that electric field E naught and it attenuates by a factor e to the power minus alpha z. If you remember that, we write e to the power minus alpha z as the electric field travels the distance, it attenuates with the factor e to the power minus alpha z. But we are talking about the power. So if we talk about the power, that is nothing but the power density, that is the peak value of electric field is square divided by 2 eta. So if I square it, I will get the peak power and also e to the power minus 2 alpha z. So that's why here it is e to the power minus 2 alpha z we are getting. Now this attenuation is given as 0.25. So we know that this 8.686 dB is equal to 1 Napier, but here the value should be in Napier. So that's why the value of attenuation which is given in dB we have to calculate it in Napier. So 0.25 dB will be equal to 1 upon 8.686 multiplied with 0.25. So from here we will get the value in Napier. So this will be 0.25 divided by 8.686, which is 0.0287. So it is 0.0287 Napier per meter. Okay, Napier per kilometer, in fact it is in kilometer. And the distance after which we have to calculate should also be in kilometer. So we have to calculate in kilometer only. And the power, so what would be the power? So the power is reduced by 40%, so the 60% power will be left. So 60% of p to the power 0, and here it was also p of 0, e to the power minus 2, alpha is 0.0287, and z we have to calculate in kilometer. So this is Napier per kilometer, so z is also in kilometer, so the kilometer will get cancelled and we get the value. So this p of 0 will get cancelled, and if I take the natural log, then ln 0.6 is equal to minus 2 into 0.0287 into z. So if I take the natural log of 0.6, this is minus 0.51, so minus 0.51 is equal to minus 2 into 0.0287 z, and this minus and minus will get cancelled, and we get 2 into 0.0287, and we are getting as z is equal to 8.89 kilometer. So the correct answer for this is 8.89 kilometer. Okay. So the last question from this chapter is, in the design of a single mode step index optical fiber close to upper cutoff, that is we want to design a single mode step fiber which should be work in the close to the upper cutoff. That means as I told you, above the upper cutoff it works only in the single mode, and below the cutoff it works in the multi mode. So the single mode operation is not preserved. So we don't want to have the step index fiber to work in a single mode. We want to have it to work in a multi-mode. That means the value of the wavelength should be in such a way that we can say it should be not crossing the cutoff wavelength, because if it crosses the cutoff wavelength, so it works only in single mode. So we have to maintain the wavelength below the cutoff wavelength. So we know that, we also know that this is let us say when lambda is greater than equal to lambda c, it works in single mode, because exactly in cutoff it works in single mode, and when the lambda is less than lambda c, it works in multi mode. Okay. And if we talk about the V number, so if the V is less than equal to 2.405, it is in single mode, and if V is greater than 2.405, then it works in multi mode. Now what is the formula for the cutoff wavelength? Because we want to have as you can see from the option, we want to have in the multi-mode, and as you can see from the option, we are changing the wavelength and the radius. So that's why we have to write this value of V, which is pi d upon lambda c and numerical aperture, and this can also be written as pi d is equal to r by 2. So this is r by 2 lambda c and numerical aperture. So we can say that V is proportional to r and lambda c. V is proportional to the radius and the lambda c. And if we don't want to have in the single mode, we want to have in the multi mode. That means when V is exactly 2.405, it works in a single mode. So if it is 2.405, then it works in a single mode. Okay. Somehow if we get this value of V, then we get this value of V, we are actually getting when we are considering all the values. Okay, so this is the case when it works in a single mode. We want to have it in a multi mode. That means the value of V should be increasing. So we want to keep the value of r and lambda c in such a way that we get the value greater than 2.405. Okay, so we want to have the value of V greater than 2.405. So this value of V, how can we increase? So there are options given to us. if the radius as well as operating wavelength are half. If I make half of these two, if r is r by 2 and lambda c is lambda c by 2, then 2 and 2 will get cancelled and we get the same ratio. As you can see from the, let us say from the option A, this V is equal to r by 2, proportional to r by 2 and also lambda c by 2. I am making this 2 half. So this 2 and 2 will get cancelled and we get r upon lambda c. So there will be no change in the value of 2.405, that is value of V, because this value of V is corresponding to the upper cutoff, and the corresponding to the upper cutoff, that is when lambda is equal to lambda c, this V is 2.405, and both are telling a single mode operation, but we don't want to have a single mode operation. So we have to take this ratio in such a way that the value of V should be increasing. So in option B, we are saying that if suppose if I make double radius as well as operating wavelength, both are double. So this is 2r and this is 2 lambda c, and this 2 and 2 will get cancelled again and we get the same ratio. So this factor r upon lambda c is constant in the two options. So this cannot be the correct one. Now if I see the option C, we are saying that if the radius is half and the wavelength is double. So what we are doing is we are taking this ratio, we are doing this, we are dividing this ratio by a factor of 4. So that means we are even decreasing the value of V, because the value of V is corresponding to 2.405, we are getting the ratio r upon lambda c, and if you are reducing this factor r upon lambda c, that means the value of V is even decreasing, and when the value of V is less than 2.405, it works in a single mode, but we don't want to have a single mode operation. So this C cannot be the correct. And now we are saying that if this R is doubled and the cutoff wavelength is also double, then we are having R upon lambda C multiplied by factor 4. So it means that now we are having the ratio R upon lambda C multiplied by factor 4, that means now this 2.405 should be multiplied with the 4, that means the value of V is now increasing. So if the value of V is greater than 2.405, it works in a multi-mode. So the option D would be the correct one. So the correct answer for this question is radius is doubled and the operating wavelength is half. So this is all about the optical fiber and the light propagation through optical fiber and the radar. So we have finished our syllabus of this subject EMT. I hope you liked it, and the overall we have discussed all the topics which is mentioned in the GATE syllabus, with the number of examples, with the number of practice questions, and even I have solved the few questions from the practice question which I found that you may get confused or you may get stuck with the solution of that question. So I have tried my best to make you comfortable in this subject. Now solve all the practice questions of this booklet and assignment questions, and then appear in the test series, and then you will find that you will be able to solve the questions from this subject as well, because these subjects are generally considered as tougher subject, or like communication and EMT, both the subjects are considered as the tougher subject compared to the others. So I hope this subject is now very good and you are much comfortable in this subject, and because I have tried that where the numerical is required, I have tried to solve many questions from that particular chapter, and where only the formula was required, I don't focused on the derivation part of that. So whatever I have covered, so please go through it and don't try to get more until you finish this part at least, because sometimes we think that the realization or the imagination should be there for this subject, but it is not easy for you guys to imagine this subject with the without just seeing some practical things in this subject. So in the normally in the college also and in the classroom also, we generally don't get that feeling like we feel in the case of signals, or maybe in the digital, or maybe in the controls. So maybe the feeling of that particular subject may not be that much strong, but the numerical solving approach is now very good, because ultimately at the end of the day you should be able to solve the questions, because in the GATE exam there will be only numerical questions from this subject. So at least you should prepare, you should be much comfortable the portion which I have covered, then only you should go for the higher level preparation. वैसे I tried that 90 to 95% of the portion I have covered is sufficient for the higher level questions also, but always there is a 1 or 2% chance that you can improve yourself. So you may follow some textbook, or you may follow some different test series, and you may get some different questions from there, and you may get the different concept from there. So you can make a note for it, and you note that with the your short notes, and you will revise it, and you try to implement with the different questions of that particular formula which you come to know as a new formula. So that is the basic idea about how to prepare this subject. So if you solve so many questions from this subject, you will get more and more confidence over this subject. Thank you.